All right. So go ahead and go to the next slide. This is kind of a slight repeat from VI week, but I think we have a little bit of a different audience. Last time, Chris had to stay up past his bedtime, and this morning I had to get up before I normally wake up. So if I sound half asleep, I apologize. And that's also why I'm not going to turn on my camera, because you don't want to see me in my pajamas and glasses. Just to let you guys know what's going on. So my name is Becky Linton, if we haven't met before. I think I see some familiar names over there from previous NI weeks. I'm a senior systems engineer and an engineering manager at Conrad Technologies in the US. I've been a certified Labview architect for, probably over 10 years now, and a Labview champion for about 5, I think. Chris, do you want to do a quick introduction to yourself?
Yeah, hi, I'm Chris Roebuck. I'm a test engineering architect at Conrad based out of the UK. I've been with the company now for coming up for 2 years, and I've been around the Labview community for a long time, I guess 20 years. Happy to be here today.
Kind of fun event. I got to see some of the stuff yesterday, and I'm really hoping to watch some of the recordings. I had a busy day yesterday with kid stuff, so it's kind of fun. And before we get started, if you want to go to the next slide, Chris. We want to start out by thanking the GLA Summit Team. Obviously, without all of their hard work, none of us would be here today. And I really did enjoy this hop-in tool. I think it's actually kind of cool, and the way we can meet and talk. So I hope that this continues in the future, or at least for as long as COVID's plaguing us. And the other interesting thing, especially about this project for me, is this was really my first large global project. And so not only was I working with the Conrad team in the US, but I was working with Chris in the UK as well as Sasha over there. And then in the Germany office, we had quite a few people. And Thomas Liebenau is a certified Labview architect that I had the pleasure of working with this time. And I've learned a lot from him. And I know some of our younger engineers have also learned a lot from him. So I just wanted to say thank you to everyone on the list there. It's kind of a fun global mix. And I hope we get to continue working together in the future. Next. For the agenda, I'm going to start out and go over the prerequisites because there is a little bit of information. We want to try to get everyone on the same page. I know this is the Global Labview Architects Summit, but this year it's open to everyone. And so even self-certified architects. So there is some advanced topics about that we're going to get into. So this is a little bit of a precursor to that, especially with the message broker. I'm going to talk about those in general. If you've never heard of them or used them, this was my first time using one on a project, and I really did like it. And I'm going to delve into the project background before turning it over to Chris. He was kind of our lead software developer on a couple of the portions we're talking about, including our modified message broker. And he's going to talk exactly how we implemented it in our software. Next. So a couple of the prerequisites, Chris, you can click again. There's a little animation thing there. But object-oriented programming, we have a lot of OO going on, especially with the actor model. DQMH, we are using DQMH modules. We're using DVRs and eDVRs. If you haven't heard of those before, we'll cover those briefly. Malleable VIs and maps. And so in order to conserve time, real quick, any of these questions, Chris is going to be monitoring them in the chat, but we can kind of go out to the breakout room afterwards and kind of do a deep dive on those. But we're not going to be able to spend an hour covering DVRs, eDVRs, or the actor model because those are separate hour-long presentations on themselves. So object-oriented programming. If you haven't done this before, I'm pretty sure most of the audience here looking at names and comments has, but there's an amazing presentation that I saw years ago by Stephen Loftus-Mercer and John McBee called Computer Science for the G Programmer. And I had taken Java in my undergrad and was like, yeah, okay, I'm not sure. I actually switched from computer engineering to electrical because I'd I'll take electromagnetic fields over Java too. I'm totally confused. And I actually felt like I didn't understand object-oriented programming until I did it in Labview. Don't ask me why. That's the opposite of everybody else in the world. But to me, it just clicked when I saw it in Labview. And there's two main things that we're fully taking advantage of here. And one is abstraction and the next is inheritance. So we're going to briefly cover those. Let's take a look at an example with an instrument. You'll see there, we have a parent class called instrument and two children, one called piano and one called trombone. And the parent class instrument has methods to play these various notes. Chris, go ahead and click. If we take a look at one of the methods of the instrument class, it actually has no code implemented. The intent here is that the behavior will be implemented in the children. So generally, instrument itself is an abstract class. the children themselves have overrides for each of the note methods that are the concrete implementations. These will play the note of the specified instrument. So why do we even bother having the abstract parent? If the child does all the work, shouldn't we just code afterwards and be done with it? Go ahead, Chris. Well, let's say we write a higher level application that plays these notes and makes it into a song. And so if we use an abstract parent method, we can at runtime call a piano or the trombone class. So here we're showing the trombone or the piano. And no matter what, what's interesting is later on, we can replace that single song, which I believe I had Baby Shark in there, but we can replace that song with whatever song you want. And we just have to make sure that the notes were already implemented in the children classes. Go ahead, next slide. The next thing I want to briefly talk about is the actor model of computation. And so there's a lot of talk about this. You hear about actor framework a lot from National Instruments. And we actually used actor framework on an earlier revision of the data logger, and we'll talk about that in a bit. But the general idea of an actor is that actors are primitives of concurrent computation. They're a little self-serving device that can go do its job, and that's it. It talks to other actors through messages, and you can have different types, and that enables the secure communication. So I know which type I accept. And when an actor receives a message, it can send messages on to other actors. It can create new actors or launch more of itself, and it can tell itself how to handle it internally and do something. And so there's a whole, there's a bunch of different frameworks and libraries. So the one thing I want to talk about briefly here is, even though we're talking about the actor model of computation, we are actually using actor-oriented design within DQMH. So Chris, if you want to go to the next slide. And so it's more than the actor framework, like I said. There's 3 excellent presentations on here that we referenced when we actually started making our own. We have a KT DQMH actor template at this point. And so our actor-oriented design, like I said, it's not AF, but we use some of the concepts from these 3 presentations. And this will be available after, so you can get to all of these links and follow them yourself. Next slide. So DQMH, I think most of you have heard of this. This is the Delacorte queued message handler. It's the expansion of the NI queued message handler project template. The key here, and one of the reasons we switched from using actor framework to DQMH, is the scripting tools, the documentation, the training, and we felt that it would be easier to bring on some of our non-architect level developers than to try to teach them actor framework. We could teach them the queued message handler. A lot of them knew that. A lot of them knew and could figure out how to work DQMH. So what we did was make DQMH actors. And there's a guest blog by Jorg on the Delacorte website that we referenced that talks about self-messaging and helper loops. Go ahead, next. So this is kind of a quick thing into our template, if you will. So we have a request and wait on broadcast message type. So that's a new thing that we implemented internally. And it still allows for a timeout, but also checks, did an error happen? Was the module requested to stop before it could reply to me? Was there some sort of emergency, nuclear meltdown, just whatever's going on in there? And the other thing we've done a lot, and you can see here, is we've actually made the module private data a class. So this helped us separate our DQMH module code from user code, so that each of our actors essentially will act and have methods upon its module private data class. And like I said, each case in the message handling loop is a method itself. And we had a few rules for our team. One of them is to not use property node for assessors. It just made it a little bit easier to figure out where everything's being used. And then the other thing you can see there, I think on the right, Chris, click one more time. You should see it highlighted. One more time. There we go, is the private API. So one of the main differences between using just DQMH by itself and DQMH actors is the private API. So the public API allows anybody to call myself as an actor and tell me what to do, or for me to, receive a request and respond to it. But the private API, we mark that, and that allows us to take actions upon ourselves. So if something comes in, I may have to queue up 5 different actions. And instead of doing it manually, we did it all through the private API so we can easily track what's happening. Go ahead, Chris. The next major technology we started using were DVRs and eDVRs. So a DVR is a data value reference. one of the big things we started using them for was memory and data copies. So on this project, we're using SeerDes cameras, which are serialized, deserialized cameras, and they have a lot of data. And we're talking gigabytes per second. And when we start including Ethernet like UDP, we have a lot of data coming in really fast. It's not as big as the camera data, but it comes in a lot faster. And then we also have automotive Ethernet. And so realistically, we have a ton of data, and we had to be really careful with memory to avoid conditions we didn't want to find ourselves in. But with DVRs, you have to use them very carefully to avoid race conditions. And then similarly, we started using the eDVRs, which are important for streaming applications. And essentially within NI, it's called a zero copy. And the idea there is it goes from the hardware device to the driver DMA buffer directly to disk or RAID without ever having to touch the Labview memory. Go ahead. Malleable VIs. So these were introduced in Labview 2017. The key here is they're very similar to polymorphic VIs, but there's no predefined list of acceptable data types. So I can make it accept, all numerics and do something with the data that comes in instead of having to implement one for I32, U8, and all the different ones. The idea is that the VI is inlined into its calling VI. Now, as we've gotten closer to deployment, one thing I want everyone to be aware of is VIMs can cause issues with PPL. So just kind of a gotcha to watch out for. We actually had one VIM that was so problematic that we ended up replacing it with a polymorphic VI. But we're getting there, we're getting through it. We did manage to get a few to work out nicely. Ooh, maps. These were one of our newer things that we threw in this summer, but they were introduced in Labview 2019 along with sets. And it's basically key value pairs in a sorted order. And we have keys and values that can be any Labview data type. And I believe Chris has slides exactly showing you some of our VIMs and maps a little bit later on in the presentation. Go ahead. So there's entire presentations out there in message brokers, and we had them on a slide earlier, but I want to go over the one we started with and kind of modified. So what is a message in general? The actual dictionary states that it's communication in writing, speech, or signals. Wikipedia, I like theirs a little bit better, surprisingly, but it's a discrete unit of communication intended by the source for consumption by some recipient or a group of recipients. A message may be delivered by various means, including courier, telegraphy, carrier pigeon, electronic bus. A message can be the content of a broadcast, and an interactive exchange of messages forms a conversation. And so I actually like that because it applies much more to the message broker that we have. It's a discrete unit. We have a recipient and group of recipients, and we deliver it by various means. Go ahead. And so in simple messaging, you pass data on a wire, and the passing of this is actually messaging. There's three components to a message to make it a little bit more useful. Is you have a type of message, some sort of transport layer, and then the address. And so if we're just looking at controls and indicators, the controls define our type, transports are the wires, and the addresses are indicators. That's where we want it to go. So I like to always take things back to a real world example. So I have two dogs. The dog on the left there is Mars, and the dog on the right is Jack. And they've been very good doggies lately. So I've decided, we've been home all summer, actually since March, right, for quarantine, and they've destroyed all of their toys. They put up with us, but they're getting a little frustrated. So I think they've ate most of their toys, and I want to get them a new one. We actually have that toy. If you have dogs, by the way, that's an excellent toy. It's really fun. It's like squirrels that go in and out. But nonetheless, we ordered this toy online from Chewy. I don't know if they have that in Europe, but it's kind of a dog store. And it appears at our house magically. How does it get there? If I got it on Amazon, it usually ships to my house on UPS or USPS. If I order it on Chewy, which is what I normally do, it almost always comes FedEx. As a consumer, I'm not going to lie, I don't care what shipment company gets me my product as long as it gets there when it was supposed to get there, right? Doesn't matter to me. So let's identify, looking at the example, what our type, transport, and address are. So our type of message in this case would be the gift or whatever I'm purchasing. The transport would be UPS or FedEx or whoever's shipping it. And then the address is my house there on the right. So let's take it back to Labview Code now. And if we look at the producer-consumer design pattern, you'll see we actually have the messaging in there. I'm not sure if you realize this, but there is messaging in the producer consumer, one of the simpler Labview design patterns. On the left there, we've identified the message and the message type. Kind of clear, right? And then as we send it, you'll see our address or our transport layer is the queue. So go to the next slide, Chris. Our type is whatever we've put in the message data. In this case, we're using a variant, so realistically, it could be any type. Our message name is our address, who's receiving it, and again, there's our transport layer. So all of this doesn't sound so bad. And if we have a few actors, and I'm looking at them on planes here, and I do want to credit John McBee. He has an excellent blog. He gave us permission before to use this information from there. But this is kind of some of the examples. So if we say the producer consumer is a single actor, that's not too bad. If we add more actors, it's not too bad. They just need to communicate to each other. However, this is what our system looks like. I actually ran the ASCII Doctor documentation tool because it does an awesome job of documenting it. If you haven't looked into that, as soon as it switches to Chris, I'll put the link in the chat. And it generated, I think it was 1,500 pages of documentation for this project. And I believe we have like 30 DQMH modules or something ridiculous. So this is what our project would start to look like if we hadn't cleaned it up. And so if you move on to the next one, what we need is some sort of central location, some sort of mediator to say, oh, this is for you, this is for you. And we've got their, air traffic control, right? So that can be our mediator. So there's a software design pattern called the mediator pattern that maps well to this airplane analogy. And here's an example here. The mediator pattern is a design pattern that promotes loose coupling of objects by removing the need for classes to communicate directly. So you and this is a whole presentation that Dimitri gave 5 years ago at the GLA Summit. And we actually used, if you go to the next one, we started out with Stream, which is a mediator pattern that was implemented by John McBee at Compose Systems, and it's online. And we also have the MVC Framework, which is kind of the next generation of Stream. We did not use that because we were not using the actor framework, but I just wanted to mention that's out there. And those are both great starting points to message brokers. A lot of times you may need to modify it to suit your needs. And Chris is going to show an example in a little bit of kind of what we've done to the message broker under the hood. So Chris, I'll turn it over to you.
Yeah, sure. So in this example, we're going to look at a very simple mediator pattern. So let's dive into some Labview code. So here we've got a simple example of a mediator. So we've got our message broker on the left that we're instantiating, and then we're passing a reference to that message broker. Here we've got a publisher, so a source of data. So I'm registering my source with the message broker, and now I'm registering several event-based receivers or event-based message transport receivers. So these two receivers are going to receive any messages published by the source. They've chosen to receive them as user events. The next two have chosen to receive their messages on a queue. So the receivers effectively say, hey, here's the message transport that I want you to use to communicate and send me data. So now we can run this and actually write some data from our data source, our publisher, and we can see that all of our receivers receive the same data at the same time, but two of them are receiving it as a user event, two of them are receiving it as a message on a queue. Back to Becky.
Talking to myself while muted. That's very common these days. So, I'm going to talk a little bit about the history of this project, because the idea of the data logger and high-speed data logger and high throughput actually originated in the US back in August of 2018. So well over 2 years ago at this point. We had a project for an automotive company, and it was just to build a high-speed data logger for some stuff that they were up to. And we're like, okay. So myself and a couple coworkers set out, and we came up with a software design based on the actor framework. We had a couple releases late December and early February that year, and then we had the initial systems were deployed. We learned a lot along the way. We actually had quite a bit of coupling between what I would call our data sources and data sinks. And that was kind of necessary because of what we were doing to enable the high throughput and high speed with the actor framework. We couldn't pass too much around, and we weren't using DVRs or eDVRs or any of that at that point in time. We had a very tight deadline, but I was actually surprised we were able to get as much working as we could. And in the meantime, we had a bunch of sales cycles happening, not only in the US, but also in the UK and Germany, with customers starting to look into, we need these high-speed data loggers and high throughput. It's not just like compact DAC logging in a car anymore. There's a lot of high-speed sensors, new sensors coming out in cars for sensor fusion and ADAS and all that fun stuff. And more customers were coming to us and coming to National Instruments. And so at NI Week, we had a big meeting. Chris was there as well, with a bunch of folks at NI, because they've been working on some of their ADAS stuff behind the hood for a few years now as well. And we said, okay, we couldn't really use your stuff yet. You're still working on it. We're working on ours. We want them to be compatible. What can we do? So go ahead on the next slide, Chris. After that meeting at NI Week, we said, as long as we made our stuff actor-oriented, we should be able to be switched with either the NI framework or a different framework or do more things. So in June of that year, Chris and Thomas actually flew to the US, and we kind of had a week-long workshop where we just hashed through a bunch of things. We said, okay, we have a couple new customers. Here's what we want to do. Here's what we're setting out to do. Here's a bunch of development rules we're going to come up with. And that's the point in time when we made the switch from actor framework to DQMH. And so by the time September rolled around, we had taken some of our original code that was an actor framework, switched to DQMH actors, and started to release things to the customer. And some of the initial systems were deployed earlier this year, and COVID hit, obviously, but we've still had a lot of momentum on this project as well as other projects, and we're still working with NI to come up with the best solution for like ADAS, high-speed, high-throughput data logging. And go ahead, Chris. All along, we had to keep these things in mind. And so we've been focused mostly on record, but we also have playback working at a minimal way. But we are using DQMH actors for modules. That allowed us to reuse as much of our actor framework logger as possible and maintain compatibility if we wanted to go back that way. We wanted to be able to support record and playback. So when we start talking about our logger, everything's very basic, and we always say data source, sync, or processor. And you might think, oh, a data source, that has to be hardware. It's giving it into my system. But that's not really true, because a data source could be a file, and a data sync could stereotypically be a file. That's where we want to save our data from our sensors to. But in the case of playback, in our mind, all that a sync is a piece of hardware that's spitting out the data that we've already recorded. So it allows us to have a very generic approach to record and playback. And then we also have these things called processors that allow you to manipulate the data either before it gets saved to disk or before it gets played back out of the system. And the way everything is set up, we wanted to allow any end sources, syncs, or processors to be injected at runtime. So you could start and stop different ones without having to restart the software. And we wanted to use classes and dynamic dispatch for our plugins so that we could bring more developers on board to build more plugins. And we tried to have very little coupling. And so that's what's going on there. Oh, go ahead, Chris. That's my alarm to wake up for the day.
You would have been late, Becky.
I know, I would have been late today.
Okay, so let's talk a little bit about the software architecture. I'm going to be concentrating on the portion down on the bottom right. If we think of that, the area inside the dotted line as being our data logging software, obviously as an interface to the outside world, to some client software to be able to stream data out or to a user interface. But we're going to concentrate on the area inside the dotted box today, in particular this area down in the bottom right called the DME. So this is our engine that allows us to configure multiple sources and syncs and the message brokers that are used to exchange messages between those sources and syncs. So at the lowest level, there are 3 plugins that can be configured by what we call the mapping engine, the DME. So the plugins are either a source. That's something that provides data to the engine. As Becky said, that could be data coming from an interface, such as a CAN card or an automotive camera. It could also be data being read from a file. So it's just a source of data going into the engine. A sync receives data from the engine, and a processor has the ability to receive data from the engine and provides data back into the engine. So we've got 3 types of modules. These are based on DQMH modules with the modifications that Becky spoke about a little bit earlier. So we've got the 3 clonable DQMH modules that are able to provide the function of data source, data sink, or data processor. So an example might be data sources typically might be video, CAN, UDP, TDMS, binary, and we might have appropriate sinks for that data. So we might be streaming video from an automotive camera to a TDMS file, for example. So the message broker sits in between our data source and data sink and is responsible for routing that data. So the sink has got no knowledge of who is producing the data. He just knows I'm receiving data of a particular type. So these connections we refer to as topics. That's what they are. The source is publishing data on a specific topic. So we might have video to binary, CAN to TDMS. But of course, we might also have a situation where we want to have binary data being received by 2 separate data sinks. So we might want binary data in 2 file formats. We might want UDP data in 2 separate file formats. We might want to write UDP not only to a TDMS file, but also to a binary file. We might want to retransmit UDP data on a different UDP port to be consumed by some third-party application. So effectively, what we've got is a flexible message routing architecture that allows us to take data from a source, pass it to various sinks or processors along the way. So what does this look like? Well, in this example, we've got a single source publishing data that is being consumed by 2 sinks. So our CAN source publishes data messages to the broker, and then each of the sinks that is registered to receive those messages or subscribe to the broker to receive those messages receives the same message. Okay, so we don't have to worry about who got the message. Anybody who's registered to receive that message will receive it. Now, where this gets interesting is when we add a processor into the mix. So a processor might be where we want to actually filter data. For example, we might want to look for a specific CAN frame as it's being received from some CAN interface, or we might want to decimate the data or filter the data for a specific channel, as an example. So in this case, we might have CAN data being published by a data source, a processor subscribed to that data source, providing some kind of filtering mechanism, and then publishing that modified data. A data sink can then subscribe to the modified CAN data. So that would be an example where we would use a processor to ensure that only certain data arrives at the sink. So a fairly flexible architecture, and since we created this, the engineers on the project have come up with some really complex topologies where we've got multiple sources going into multiple processors, each processor filtering specific elements of data that they're interested in, and then piping that data to specific sinks that only are interested in certain attributes of that data. So an example with a processor would look something like this. CAN source publishes data to the message broker, processor subscribes to that message broker and receives the message, performs some modification to it, and then publishes data that is then subscribed to by a sink. So a little bit of acronym and terminology, because I'm aware I've been kind of injecting some of these phrases already. So a module is effectively a DQMH actor within our system. So it might be a data sink, a data source. It might be the mapping engine itself, which is also another DQMH module. Our DME, our mapping engine, simply configures a runtime collection of sources, sinks, and processors. So that's the key point that I want to get across to this, is those configurations between sources, sinks, and processors is a runtime thing and can be defined via a text file or a configuration, and the DME is responsible for instantiating all of those different modules and message brokers and ensuring that the messages go the right way, if you will. So a topic is basically a group of sources, sinks, or processors. A mapping is a group of topics. A collection is a group of mappings. So we've got this hierarchical complexity here where we can have multiple topics connecting various sources to various syncs. And like Becky said, sources might be hardware, but it might also be a text file or even a UDP port. Who knows what it is? And a plugin is any child. So the mapping engine is able to launch sources, syncs, and processes, and they have some basic methods such as read, write, initialize, open, close, and that enabled our developers to simply create plugin modules that would inherit from the parent source, sync, and processor module, and not have to recode everything, but instead concentrate on the key methods that are required in order to build behavior around whatever interface they're trying to develop a plugin for. So if they're writing a UDP plugin, then they just need to write methods to override the open function, the read function, and the close function, so that they open a UDP port, they read from it, and they close it afterwards. And the parent DQMH module effectively is reused, and we inject that plugin at runtime to say, okay, this source, you are a UDP source. You need to call these methods relating to UDP. So let's see a little bit more what that looks like. So I've got some examples here with some actual Labview code. So let's take a look at that. So we've got a topic here, which is a single source and a single text sync. So I'm reusing an example from VI Week earlier in the year. I apologize to the GLA Summit organizers that I wasn't able to re-record these videos, but I think they get across the point really well. So we've got a single UDP source and a text sync that is going to be instantiated. So let's take a look at what the code looks like for that. So let's have a look at the block diagram. Oh, I did some fancy Zoom at the time. Yeah, that probably all went horribly wrong. So here we've got our API for our message broker, or our data logger, if you will. So here I'm creating a topic. It's called demo topic, and I'm adding a source to that topic. In this case, a UDP source. I'm adding a sync. In this case, a text file. Just pause the video for a second. We can see over here on the left, we've got some configuration that is also passed in. When we add the source and we add the sync, we pass in some configuration information. So for the UDP, it's a JSON string telling us what the port number is, the connection timeout, etc. For the text file sync, the JSON string relates to the actual text file that we want to save. So in this case, it's a path to a text file that we're going to generate. We then run the source and the sync modules, and they're effectively going to be instantiated, configured, and we'll wait for data to appear on the UDP port. Any data that appears on the UDP port will be sent to the text file, and then we close the thing down afterwards. So let's go ahead and run that. On the right-hand side, I've got a couple of simple UDP senders just to generate some data that we can send. So here we're listening on UDP port 61557, and we're going to go ahead and generate some data on that port. So let's run that now, and let's generate some data, and let's just send the string VI week. And let's send it a couple of times, and then let's stop our logging framework and have a look. And there's our text file that was created, and there we can see a timestamp and the string data that was received on the UDP port. So simple demo just with a single data source, which was a UDP listener, and a single sync, which was a text file. Let's look at something a little bit more complicated. Let's look at a single source with two syncs. So I'll skip ahead, get to some. So here we've got a UDP source and two syncs. So looking at the block diagram, we can see a little bit more complex, but very, very similar. In this case, we're just adding a second text file called text file 2 to the same topic. So we've got a single UDP listener and then two text files. So what we should see now when we run it is two text files being created. And if we go to our UDP sender, we'll see our two text files both contained the same data with the same timestamp. So the data that was received on our UDP listener was then sent via the message broker to both of the syncs that were instantiated, and they both received the same data. So useful perhaps if you want to save data in a couple of different file formats. For example, one customer requirement was to have multiple file formats to store effectively what was the same data being captured. So that's
Real quick, you didn't mention there with the timestamp to the left of it, there's the message index as well, right?
Yes, yeah, that's a good point, Becky. So I think if I just jump ahead to where we actually look inside, yeah, so we've got a little bit of information there. On the far left, we've got a message index, which was I guess a way of showing to the customer that both of the syncs were receiving the same data in the same order, irrespective of the timestamps being the same. They wanted to say, okay, show me that the same message is received and the order is guaranteed throughout the framework. So the customer was not a Labview house, so they didn't really understand queues and various mechanisms we've used, so we had to actually put some checks and balances in the data that we save as well. So I don't know if there was anything else you wanted me to mention there, Becky.
Just wanted to make sure that that was important to the customer and us, that we didn't lose any messages within our message broker, and that was kind of the way we tracked it, was with that message index.
Yeah. So another example, so as I mentioned, this thing's a kind of a runtime configurable situation. So another thing that we might typically want to do is to say, okay, well, how about the situation where I've got two sources and a single sync, in which case I want to aggregate data into a single file. So I think in the particular case the customer was interested in, they wanted to listen for data on two UDP ports. They didn't care whether the data was interleaved as such. They just wanted to listen to two UDP ports and capture all of the traffic in a single file. So here we've got an example. I jump ahead to the big block diagram. We've got a single file that, sorry, two sources. So we've got a single topic called demo topic, and we're adding two UDP listeners in this case. So we've spun up two source modules, and we've configured them to be UDP source modules, and they're both going to listen on different ports, but we've only added a single text file to that topic. So any data captured by those two sources will be aggregated into a single text file. So let's go ahead and run those. We've got two dummy UDP senders on the right hand side, both sending different messages. So we'll send a few messages. Let's stop that and have a look. We've got a single text file that's been created, and there we can see our messages, and you can see that the data was aggregated with timestamp, but the data was aggregated from multiple data sources, in this case, into a single destination. So that was another configuration that the customer wanted to be able to do. And again, they want to be able to vary all these different permutations of source and sync. So they might have some sources aggregating data. They might have some sources simply going on a one-to-one mapping between a source and a sync. And then the final one, and this is the one that's proved to be the most useful, is the processor module. So the ability to have a source, have that data be processed in some way, and then have syncs subscribe to that data. So in this particular case, what we're going to do is we're going to have one sync subscribe to the raw data and a second sync subscribe to the processed data. So let's take a look at that one. So let's just have a look. We're going to receive, again, using our UDP example, we're going to receive string data on a UDP port, but in the top left, we can see our actual processing method. So here we're receiving a message in. We're converting the message to, well, it's a string message because we're receiving UDP data. We're going to make it uppercase, and then we're going to rebroadcast it back out to any syncs that are subscribed to receive it. So here we've got a more complicated block diagram, obviously, because now we've got two topics. We've got a data topic, which is the raw data from UDP, and we've got a second topic, which is the process data that was received by our processor. So a more complicated block diagram. Again, keep in mind, these are demonstrations, our mapping engine is able to configure these dynamically at runtime. But for demonstration purposes, it's nice to just see what the API really looks like. So we've got a data source and a sink, the sink receiving the raw data, and then we've got a text processor and converting it to uppercase, and a sink that is subscribed to the data that's been processed. So let's jump ahead and run that, and here we can see we're going to go ahead and run our UDP data. So we're sending VI week multiple times. We can see we've got two text files. One will be raw data, one will be processed data. So let's take a look at that. So that's our raw data, and that's our processed data, one of which was converted to uppercase. Notice that the timestamp of the data is the same because that was the timestamp where the data was captured into the system by the source. It was then subsequently made uppercase, it was subsequently processed, and then written to text file. So the idea of this is that we can have multiple different permutations of source and sink configurations. So that's our processing node. So let's have a look at some of the underlying architectures. So our message object, we saw from the processor that the processor receives an object, a message object. So what does our message object look like? Well, it's got some data, it's got some metadata associated with it, timestamp information, for example. It's got an ID, a unique ID, so that we can track every message throughout the system, and a session ID, so that we know, okay, this data was produced by a particular source or a particular sink. So in this case, consider the data to be by value data. We also have a message object, which is a DVR-based message, where we don't want to send the data throughout our entire framework. We just simply want to send a reference to that data. In this case, our message ID becomes a little bit more complex and has a little bit more information. So that's a look at building a by value message, where we take a value, some format information, and a timestamp, and our output is a by value message. Okay, so for high throughput or very small data size messages, we send those by value because the overhead of creating a DVR maybe doesn't give us the benefit, and the memory footprint of the messages themselves is significantly small. Maybe we have a single topic that is one source, one sink, very small messages being sent infrequently. By value is absolutely an acceptable means of doing that, and from a performance point of view. But for messages with a large data payload, such as LVDS data, where you have several gigabytes within a second or two, then these are sent as by reference messages using a DVR or eDVR, and we'll explain a little bit about that and that journey also. But in that case, the message object doesn't contain by value data, it simply contains a reference to that data. Okay, so that's our DVR. Just to quickly show a kind of a sneak peek here of a more recent investigation and development pathway, shall we say, was to use eDVRs. So in this case, we've allocated a block or a byte array, a reference to a byte array in memory, and then written a string to that in-memory block of data. The nice thing about the eDVR is the ability to then pass the eDVR reference directly to, in this case, write to binary file. So if zero copy is something that you're looking to achieve, then DVR or eDVR works nicely. But obviously, there's got to be some management in there. So knowing and acknowledging the receipt of messages is critical, because if you don't acknowledge the receipt of a message, you don't know if it's safe to reuse that block of memory, or in the case above, to release the DVR, the data value reference. So in our case, we've got an asynchronous module that's managing all of the DVRs, the number of receivers, and when a DVR is received by a sink, we are able to acknowledge that it's been received, and if it's been received by everybody, then we say, okay, well, in that case, it's safe to be removed or reused in the case of the eDVR. So there has to be active management of these references within a reference-based system, especially when data throughput, memory size or memory footprint and CPU cycles are critical. I mean, we're talking about many gigabytes per second through this system. So management of these DVRs is critical. In order to provide developers with tools that would enable this framework to be accessible, this was one of the engineer that Becky mentioned, Thomas. This was one of Thomas's suggestions, was to actually, okay, well, just provide malleable VIs for building and decoding messages that can adapt to different data types that are wired to them. So a developer can take a build message and wire anything to it, and then on the decode side, he can take a message object, wire in an expected data type, and pull the data out of that object, obviously provided it's the correct type that's been wired. In addition to that, we also use the type specialization structure to allow these to allow the passing of classes whose private data was slightly different. So for example, a processor or a sink have slightly different private data, but we wanted to be able to reuse the build and decode messages not only in sources and sinks, but also in processors. So the type specialization structure was able to give us that. I have to say, malleable VIs, every time I see this, it still sends shivers up my spine. The fact that I've got broken wires and the run arrow is not broken. Yeah, that still messes with my head every time I see it. But thanks to Thomas for pushing us in that direction. It's definitely been of benefit. The other thing we used was maps to keep track of all of the message IDs across multiple source and sink combinations to make sure that we were not missing messages and that they were arriving in the correct order. And what we found was that certainly for numeric data types, there was some significant performance gains to be achieved over lookup tables. With other data types, I think some of those performance gains are maybe not as impressive. We're using Labview 2019 as well. I've been told on good authority that 2020 brings further improvements to maps and fixes a few things as well. So that's something we'll be looking out for. So, okay, Chris, you've shown some abstract block diagrams of messages and some API block diagrams, but what about the actual thing running? So we're going to finish by having a quick look at our mapping engine. So we have a much prettier UI that sits on top of this, but this is kind of a tool that we use internally to say, okay, I want to load a collection of sources and sinks, and it might be multiple sources and sinks and processors, and they're all defined in what we call a mapping file, which is just a huge JSON file that instantiates all of the sources, all of the sinks, configures them, and sets them running. So in this case, we've got a very, very simple mapping that launches a UDP listener and a text file endpoint. So it's going to listen for UDP data. The point being, this is all configured on the fly, so we can just change that UDP mapping to be a CAN mapping or to be a combination of both. Some of our mapping files have upwards of 20 topics with different data sources. So we can see our topic is idle. We've got a UDP actor, a text sink, and a UDP processor in our system. So we've got two topics, a processed UDP and raw UDP. And let's go ahead and run that thing and see it in action. So let's start all topics. We see their status changes to logging, and now we can go ahead and let's type some string in there and broadcast it over UDP. Little typo. Let's run that. I type way too slow for demos. Let's run it lots. Let's stop it. Let's tear down our logger. Let's stop all of the topics. They've all gone idle. Let's remove them from memory. And then let's go ahead and have a look at the two text files that have been created over here. And we've got our raw data. And we should have our processed uppercase data. Now, obviously, UDP data and text files is a pretty contrived example, but without hardware and doing demos on video, I think it gives a pretty powerful demonstration. So I think in terms of everything, that's all we've got. Obviously, there's a breakout session where people can ask questions. I think we're pretty much coming up on time anyway. But if we can go into breakout sessions, if people have got questions, we'd be happy to answer them. Becky, I don't know if you've got anything else other than to just say thank you to the organisers as well. This has been great. Loving the tool, loving the organisation. I think it's been fabulous for all of us, desperate for a Labview fix.
Oh, yeah. The one more slide, just so everyone knows that in the presentation, which we made available, there is a single slide with all the links we have in there. And so the only other thing I added is there's a link in the chat for the tool that we were using, the anti-doc tool. So I think others might find that helpful as well. But we kind of tried to put everything in one spot because we referenced a lot of other material. I don't think we'd have gotten as far as we did without all the other presentations Chris and I have seen over various CLA summits and NI weeks, and trying to put all this stuff together and say, can we make it work?
Okay, so I'm going to head over to the breakout sessions if anybody's got any questions.
Yeah, it looks like there's a couple that are popping up, so we'll answer them over there. There's about some performance monitoring for processors and so forth.
Yeah, okay. All right, thanks everybody. Thanks, Becky. Sorry to have woken you up so early.
Oh, it's okay. I'm more awake now. I'm good. I had my first Diet Coke.
Talk to you soon. Thanks everybody. Stay safe. Bye.